So here's the definition. We define the directional derivative of a function in the following manner. Let's say that the directional derivatives in the plural form. And I'll jump right into three variable functions. Of course, you can reduce everything we discussed so far to two variables, but the principle is exactly the same thing. And now we're looking for a particular direction. So in the direction of a unit vector u, it's given by the dot product. So what is the dot product? Well, it's a dot product between the gradient and the unit vector. The notation is d sub u. So this will give you the derivatives in the direction of u, and it's an operator. D sub u is an operator, and it operates on a function f, in this case function in three variables, and this will be defined as the gradient of f dot the unit vector u. Okay. If you want to specify that, or you break it down to the component, well, here's the gradient with its three components in the ijk direction. The unit vector u is, let's say, component ABC. Then when you break it down, you end up having the following. I'll drop the x, y, and z, but it will be the dot product okay, so you have this, and we dot product it with the vector component ai plus bj plus ck, like so, right? So what is the result? Well, the result will be a times del f del x. The result is a dot product, so it's a scalar, plus b times del f del y plus c times del f del z. Okay, where u equals ai plus bj plus c k is a unit vector in some direction. All right, so I think we're good for an example. Yeah. It's like in the previous example, it said let's find the slope of it on this topographic map in the southwest direction. So we looked at the particular direction. Let me just make a comment about this du. D is a derivative operation that we use it rather commonly. So here's a comment. The letter D, well, it's used. We have a lot of D's in mathematics. You have discriminant, determinant. We have all kind of stuff. But when it comes to calculus, a lot of time we use D as a differentiation operator. So let's write a comment here. D is often used as a differentiation operator. For instance, d sub x is del x. Okay, it's a derivative in the x, the partial derivative in the x direction. D sub y, of course, will be the same thing, and d sub z will be the derivative with respect to z. Okay, and in this case we have d sub u is the derivative in the direction of u. Again, it's defined as the gradient of vector f times a dot product u. So it's the directional derivative. So that's why the letter D is used in this manner. Which A? A, B, C? Those are the direction number of the unit vector. So it's right there. It's built into the U. Those are the vector component of U. Make sense?
Yeah.
Good. You'll see the example coming on, and you'll see the first one. It will make sense. The first one, I think, it's a two-dimensional. Is example in X and Y. Question, Joe, or just stretching? All right. You need another few seconds to look at this paper? See, Chris is still writing. All right. I'll start writing the example here. So this is the first example, and let's look at the function f of xy is x e to the xy plus y. Okay, this is given, and what we are required to do is find the derivative, the directional derivative du at f for the specific point where x equals 2 and y equals 0 in the direction. Let's do negative 1 and square root of 3. In the first order is to find the gradient vector. Okay. So in general, we're going to say that the grad of f of xy will be del f del x in the I direction plus del f del y in the j direction. So what is the derivative in the partial derivative with respect to x? Well, we need to have a product rule here. So the derivative of x is 1, so we have 1 times e to the xy plus x times the derivative of e to the xy. Well, the derivative of e to the xy is y e to the xy. Okay? And then plus the derivative of y with respect to 0 is 0, so this is pretty much what we have in the I direction. What do we have in the j direction? Well, the derivative of x e to the xy with respect to y will be x times x, so will be x squared e to the xy plus 1. And we can simplify it somewhat, pull out the e to the xy. We might as well leave it like that, because now we are interested to find the gradient vector at 2 and 0. Okay? So what happened in this case? When x equals 2 and y equals 0, then e to the xy becomes 1, and here we have 2 times 0, so it's simply 1. So we have 1 plus 0 in the I direction. And here we have 4 times e to the 0, so 4 plus 1, so 5 in the j direction. So we end up I plus 5j. Bless you. Okay, so this is the gradient vector at this particular point to 0. Okay, so it has a component in the I direction or in the x direction, a component with the j direction. Now we need to look at the unit vector. Okay, so what is the unit vector corresponding to this? So if the unit vector will be I'll do it in ij component. Well, we have negative I plus square root of 3j divided by the magnitude. So it's the square root of negative 1 squared plus a square root of 3 squared. So we have 1 plus 3, that's 4, square root of 4 is 2. So we end up having negative 1/2 in the I direction plus a square root of 3 over 2 in the j direction. This is the unit vector. All right, so now we are ready to complete the task. We're going to say that the directional derivative in the direction of u is the dot product is the gradient at 2, 0 dot the unit vector. So we have I plus 5j dot negative 1/2 I plus square root of 3 over 2j, like so. So what do we have when we do it? We have negative 1/2 plus 5 square root of 3 over 2. So we have 5 square root of 3 minus 1 over 2. So what happens if you don't take the unit vector? You have twice as much because you lose the 2 in the denominator. So you artificially inflate that particular value